A final example for this section. This is 7 videos, which is more than I'd like for a section, but there's so many different types of examples to see with cylindrical and spherical coordinates. I want to show you different types of things that are there, and I want to create a nice library of examples that you can refer to. This one I want to show you just because the function that we're dealing with is a little bit different. And we're going to have to figure out what that is. We know what this surface is. E equals the square root of x squared plus y squared is a cone. We've been dealing with that, but we're not so sure about the other surface. We are integrating the function 1, which means we're computing a volume. Only when we're integrating 1 in a triple integral do we get a volume. So we know we have a cone. Let's see what the other thing is. X squared plus y squared plus z squared equals z. In spherical coordinates, x squared plus y squared plus z squared is rho squared. And z in spherical coordinates is rho cosine phi. So I've replaced my variables with spherical coordinates, and this is the reason I wanted to show you this example, is that you can take an equation of a surface in rectangular coordinates, and we can replace the rectangular coordinates with whatever they are in spherical coordinates, and we get a version of the surface or of the equation in spherical coordinates instead. So rho equals cosine phi. That's the thing that we're dealing with here. That's our surface. That's the surface in spherical coordinates. I still don't really know what this surface is. And to explore that, if I go back to rectangular coordinates, x squared plus y squared plus z squared, if I subtract z from both sides and complete the square, then this is x squared plus y squared plus z minus 1/2 quantity squared equals 1/4. This is a sphere of radius 1/2 centered at 0, 0, 1/2. So that's what we do have. We do have a sphere after all, which makes sense because it's a spherical coordinate example. And so what is our shape? We have a cone below. Everything above this cone. Oh, do better than that. And everything below this sphere. So the sphere is the sphere centered at 0, 0, 1/2 with a radius of 1/2. So that's our sphere. And guess what? It's another ice cream cone, just a different one than what we've been doing before. In the previous problems with ice cream cones, we had the sphere dipping below the xy plane. In this case, the sphere is sitting on the xy plane. And now we've got everything we need to set this up and do this problem. The cone is still phi equals pi fourths, like in our previous ice cream cone problem. The sphere we just saw is rho equals cosine phi. And so we have an integral from 0 to pi fourths, 0 to 2 pi for theta. We go all the way around, 0 to cosine phi for rho squared, sine phi, d rho, d theta, d phi. I'll do the theta integral because there's no theta dependence anywhere. That's just going to be a constant 2 pi. We'll have our 0 to pi fourths in phi. For rho here, we get rho cubed over 3 from 0 to the cosine of phi, sine phi d phi. That's going to be 2 pi over 3, integral from 0 to pi fourths. I have a cosine cubed phi times sine phi d phi. We can do this with a u substitution. U equals cosine phi, then du is minus sine phi d phi. And that means we have minus 2 pi integral from well, if phi equals 0 to phi equals pi fourths of u cubed du, and that is going to be a minus 2 pi. U to the fourth over 4 is going to be cosine to the fourth of phi over 4 from phi equals 0 to pi fourths. And let's see, that's a minus 2 pi over 12. Cosine of pi fourths is 1 over the square root of 2. If we square that, we get 1/2. We square that again, we get 1/4. So 1/4 minus the cosine of 0 is 1. So that's a negative 3/4 minus 2 pi twelfths times minus 3/4. 2's cancel. 3's cancel. It looks like we have pi and negatives cancel, so we have pi over 8. Makes sense to get a positive answer because this is a volume. We were integrating 1 and everything was above the xy plane, so it makes sense to get a positive answer. That's nice. The answer is pi eighths. This is just another spherical coordinate problem, but there's some interesting things here, right? We had to do work to figure out what surface we were dealing with. And that work involved algebra and completing the square to see that we had a sphere. And then we had to take that sphere and try to write it in spherical coordinates. So we replace all the x, y, z's with rho, theta, phi stuff. We figured out the equation of the sphere in spherical coordinates. We already knew the cone. That gave us all of our endpoints of integration, and then it was just integrating, which actually involved a u substitution, so quite a bit of work to get to the final answer on this one, but we got there.